Our last section here for Unit 9 is called Electron Configuration. It's going to explain something you've probably seen on your periodic tables, but haven't had an explanation for yet. When it comes to electron configurations, we've actually kind of started this a little bit in the previous section when we were talking about principal quantum numbers and the different sublevels and the shapes of the orbitals with s, p, d, and f. Each of those things has certain energy levels associated with it, and electrons are going to favor filling in those orbitals in the lowest possible energy arrangement. So they're going to favor the ones with the lowest n values in certain orbitals first. We'll see how it fills in here shortly. This is going to lead to the most stable arrangement. Now, electrons can get bumped up to higher energy levels, which we talked about last time, and that's by absorbing photons. But they generally try to stay in their lowest possible energy arrangement. There are three rules that govern how electrons fill in the orbitals in the different principal quantum numbers. Those are the Aufbau Principle, the Pauli Exclusion Principle, and Hund's rule. So those are the three that we're going to talk about in this section. Okay, so the first one here, the Aufbau Principle, is basically this, that each electron occupies the lowest energy orbital available. We'll see here in a moment that there's a particular order these things go in, right? We said before that the lowest energy arrangement or orbital that an electron can be in is in the 1s orbital. And then it will be 2s, and then 2p, and then 3s, and then 3p. And we'll see sort of there's a pattern here that forms. It's not all just s, s, p, and the numbers increasing. We'll see sort of what that pattern is here in a moment. But there's a sequence that you'll need to learn of the atomic orbitals from the lowest energy to the highest energy, and we'll show you kind of a shortcut to memorizing that, plus your periodic table will help you quite a bit. Okay, so what are these orbitals in order of increasing energy? Well, 1s is the lowest energy, then 2s, then 2p, 3s, 3p, 4s, and then 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. Okay, so we'll see sort of how this pattern all fills in here, but this is the increasing energy of each of the orbitals. So you can see there's actually a very large difference between 1 and 2, and then as we kind of go up here, the levels become closer and closer together in energy level, but they are separated out into these different orbitals and principal quantum numbers. Okay, so here's a useful tool to help you remember if you're ever not sure like what comes next in terms of energy levels. Okay, so we've got going down here in this far left column, we've got 1s, 2s, 3s, 4s, 5s, 6s, and 7s. Technically 8s is for elements that we haven't found yet or aren't able to find because they just don't exist. So really it would stop here at 7p, but theoretically, right, it could go on to 8s. But notice our far left column is s. The next column is P, and it starts on the second one. The third column is D, and it starts on n equals 3. The fourth column is F, and it starts at n equals 4. Okay, and so the order in which these things fill is kind of a zigzaggy line passing through all of these here. Okay, so it starts at 1s, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s. So you can kind of see how this pattern works here. So if you ever forget the order, if you're able to draw this out, right, with s from 1 down to 7, p from 2 to 6, d from 3 to 6, and f from 4 to 5, and just kind of fill in this zigzag line here, you can always remember what orbitals come next. And remember also that each orbital can hold a maximum of 2 electrons. So we'll see kind of how this all fills in here and how many electrons we end up with when we get down here at 7p. Okay, so a couple of questions for us here. Which sublevel has the greater energy, 4d or 5p? Well, I've kind of quickly sketched out what that Aufbau filling up principle looks like here. And so if we follow through our lines, if we draw them in, coming in initially at 1s, right, coming back to 2s, 2p, 3s, okay, 3p, 4s, 3d. So you can kind of, even if you forget the pattern here, you can work like this. So we got to 5s, this comes all the way back around to 4d, and then 5p. So the one that's technically at higher energy here is 5p, okay? It's further along down our chain, okay? So why don't you try this one here? Which sublevel has the greatest energy, 6p or 4f? And consult this up here if you're not sure. You'd have to keep filling in the lines like I have. Okay, so if we fill this in all the way out, okay, until we hit both of these, we keep going. It goes 4f, 5d, 6p. So these 6p orbitals, okay, have greater energy than the 4f orbitals. Okay, so the second one we need to talk about here in terms of electrons and their rules is the Pauli exclusion principle. And so let's start with this by saying that electrons in an orbital can be represented by arrows and boxes or on lines. Generally, what they look like is either half arrows pointing up or half arrows pointing down. Sometimes you'll see people write them with a double-headed arrow, but most frequently you'll see these kind of half arrows drawn. Each orbital can only have 2 electrons as a max. And each one spins in different directions. So one would spin with a positive spin and one spins with a negative spin. So plus 1/2 or minus 1/2 is technically what we call it here. And so that they counter each other. So you can't have more than 2 in here, and they must be spinning opposite directions, which is why these arrows point in opposite ways. So the Pauli exclusion principle states a maximum number of 2 electrons can occupy a single atomic orbital, but only if the electrons have opposite spins. The maximum number of electrons at an energy level is still 2n squared. Okay, so let's show you what this looks like in practice. Let's say we have, just an atom with a single electron. Okay, well, it's going to fill in at the lowest energy level. It's going to fill in here, and by default, we'll usually give it the plus 1/2 spin, so it usually points upwards. If we have an atom that has 2 electrons, the second electron is going to fill in, because this orbital can hold 2 electrons. It's going to fill in that first orbital, but it's going to have the opposite spin, so it'll be pointing in the opposite direction. Once you have 2 electrons, this orbital is filled. Okay, so we can't put any more in here. And so we go along, okay, following our initial Aufbau principle to the next one, which is 2s. Okay, so if you had 3 electrons in an atom, the third electron would be in the 2s orbital, and it would have the positive spin. And then if we had 4 electrons, it would also fill into this 2s orbital as well. Okay, both having opposite spins. We're going to show you what happens here in a moment when we have multiple orbitals. Remember, there's 3 p orbitals. There's the x, y, and z orbitals for these right there, the dumbbell-shaped ones. Okay, so we have 3 of them, and each one can hold 2, so we can fill in 6 electrons here. We're going to see how we actually fill this in properly here in a minute. Okay, but there's a way to do this technically where you fill each of them once before you fill any a second time. We'll learn about that principle here in just a moment. But that's how this fills in. Okay, we would just keep following this on up. Remember, d orbitals have 5 possible ones. F orbitals have 7, okay, total orbitals. All right, and the last rule here, Hund's rule, this is what I was alluding to just a moment ago. Single electrons with the same spin must occupy each equal energy orbital once before an additional electron with opposite spins can occupy the same orbital. So we're going to say we're filling in p orbitals with 6 electrons, okay? All right, so these are p orbitals. We can call them 2p, 3p, doesn't matter. There's 3 different orbitals there, and we're going to fill them in with 1, 2, 3, 4, 5, and 6 electrons. So the first electron that would go into a p orbital would just be in the first one there with a positive spin. If you had 2 electrons, the first one goes into that first orbital. The second one goes into the next one with the same spin. Okay, that's what this is saying here. All right, we're going to fill in all 3 of these once before we fill any in a second time. With 3 electrons, we're going to put 1, 2, 3 in like that, each one with the same spin. Now that we have 4, okay, we're going to go 1, 2, 3, and now the fourth one, okay, pairs up here with our initial one with the opposite spin. Okay, so you can see kind of what Hund's rule means. 1, 2, 3, 4, 5, and then 6, 1, 2, 3, 4, 5, 6. So we've got the Aufbau principle, which tells us the filling order, right? 1s, 2s, 2p, 3s, 3p, okay, and so on down the line. We got the Pauli exclusion principle saying we can only have 2 electrons maximum per orbital, and that they have opposite spins. And then we have Hund's rule here, which says we fill each orbital once before we fill any one a second time. Okay, so let's do this for carbon. Carbon has a total of 6 electrons, right? Its atomic number is 6, so it's got 6 electrons. How are these going to fill in? Well, the first 2 electrons are going to go into the 1s orbital. Okay, it's the lowest energy level, and they are going to have opposite spins. The next two go into the 2s orbital, all right, with opposite spins. I have two more electrons that need to then fill in within the 2p orbitals. So the first one, electron number 5, will go into the first orbital, and electron number 6 will have the same spin going into the next orbital. So that's what it would look like for carbon. What we then call an electron configuration is if we take all of these, okay, and write them kind of in a shorthand notation to say where the electrons are. Okay, I've got 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and 2 electrons in the 2p orbital. And how we write that looks like this, okay? 1s2, 2s2, 2p2. That tells us where the electrons are. And this is called the electron configuration. And if you look on your periodic table, you might see this. You might also see something like He, 2s2, 2p6 as well. We'll talk about what those are. All right, but essentially what each of these are, the first number is the principal quantum number, the S is the sublevel, right, or the shape of the orbital, so S is spherical, P are those dumbbell shaped, and then the thing that looks like an exponent, the superscript, that's the number of electrons in that one, so 1s2, 2s2, 2p2 matches up with what you see here. So see if you can see that on the periodic table as well. A lot of the periodic tables will have these electron configurations, or a shorthand version of it like this, which we'll see in a moment. Okay, so here's what it looks like for the first 10 elements, right? Hydrogen through neon. Atomic numbers, so you got 1 electrons, 2, all the way down to 10, and where they would go. The first one, right, for hydrogen is 1s1 would be its electron configuration. Helium would be 1s2. And notice that's the end of the first row of the periodic table. And we filled in all of our n equals 1 values as far as we could. Then we go down to lithium, the start of row number 2. 1s2, 2s1. Beryllium, 1s2, 2s2. And then we've also got 3 p orbitals that need to fill in with 6 electrons. Okay, so then you've got boron, 1s2, 2s2, 2p1. Carbon, 1s2, 2s2, 2p2. Nitrogen, 1s2, 2s2, 2p3, right? All the way down here to neon, okay, with 1s2, 2s2, 2p6. And those of you who are paying attention would note that right at the end of helium, this is the end of row 1, and down here with neon, that's the end of row 2. So that is actually kind of, you might start seeing a pattern forming here. You might be able to guess then that argon is going to be the end of row 3 because it's going to fill in the n equals 3 level. Okay, so I'm going to do a couple of these with you, and then I want you to try a couple of them on your own. We're going to call this the ground state electron configuration, where we write everything out from 1s all the way to the very last electron. Let's start with, this one is bromine. Bromine is element 35, right? A neutral atom of bromine is going to have 35 electrons. Okay, and I would have handy your Aufbau Principle chart, and then we'll make sure we pay attention as well to the other rules as we fill stuff in. Okay, keep in mind that s orbitals can have a max of 2, p orbitals can have a max of 6, d orbitals can have a max of 10, and if we get that far, f orbitals can have a maximum of 14, right? 1 orbital, 3 orbitals, 5 orbitals, and 7. Okay, so bromine's got 35. Let's just start going through our charts, okay? We've got 1s first, 1s2. Okay, so now we're down to 33 more electrons needed. The next thing that comes up is 2s. We've got 2s2. Okay, now we're down to 31 more. Then we're going to have 2p6. Okay, so now we've used up a total of 10 here. We're down to 25. After 2p on our Aufbau principle is 3s. Well, we can fit a maximum of 2 in that. Now we're down to 23. We're going to have 3p6. Okay, so now we've got all the way down to 2, 4, 10, 12, 18. So we've got 17 electrons left to go. After 3p is 4s, as called a maximum of 2. Now we're down to 15 left to go. After 4s is 3d. Okay, and d can hold a maximum of 10. So now we're down, okay, towards the end here, we're down to the final 5. And notice our next one would be 4p. Okay, and up to this point, if we've been keeping track, right, this is electron number 30 at this point, right? Okay, we've got 5 to fill in here. We can hold a maximum of 6, but we've only got 5 left to go. So we're going to finish this off with 4p5. Okay, let's do SB now. SB is antimony. It's got an atomic number of 51, so we're going to need a total of 51 electrons to fill this in. Well, we can kind of, maybe do a little bit of easy work here, because the start of this is going to be very similar to bromine, okay? We can just start filling that in. We've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Okay, now if we do 4p6, we're up to a total of 36 electrons, and that 4p orbital is now filled. So let's keep going. We got to get out to 51. After 4p is 5s. That can hold 2. Okay, now we're up to 38. I'll keep a running tally down here at the bottom. After 5s2 will be 4d10. Okay, and that gets us up to 48. So we're getting close. And the last one here, so now we're up to 5p. We don't need all 6, we only need 3 of them to get us to 51. So that would be our ground state electron configuration for bromine and antimony. I'm going to give a couple of them for you to try now. Okay, so the 2 for you to try here, sulfur and iron. Let's see how you do. Make sure you've got your periodic table handy. Okay, so here are the solutions for you. Sulfur needs 16 electrons, should look like that. Iron needs 26, should look like this. Okay, so your periodic table might also have this listed as what we call a noble gas notation. So this is kind of a shorthand way of doing these electron configurations. It's a method of representing electron configurations using noble gases. Noble gases have a completely filled in value, right? So if you look at the far right of your periodic table, each of those has completely filled in, all right, the end of that particular in level. The outermost 8 electrons are very stable, right? You've got the 2 from the s orbitals, okay, and then you've got the 6 from the p orbitals at that same, whatever that n value is. So they represent noble gases. We can represent noble gas configurations by using brackets, which I showed you earlier. So, for instance, right, helium, if you see it in brackets, that's representing the configuration 1s2, or neon represents the configuration 1s2, 2s2, 2p6. So previously in that example with the sulfur was 1s2, 2s2, 2p6, 3s2, 3p4. Instead of writing the whole thing out for sulfur, what you might see instead is you might see neon in brackets like that, and then you would see 3s2, 3p4, and it would save the person having to write all of this beginning, okay? So this is called a noble gas notation. So here's another example. We can shorten other elements. Sodium isn't necessarily written as 1s2, 2s2, 2p6, 3s1. Your periodic table will probably list it as neon 3s1, okay, because the neon's going to account for the first 3 of those there. So I want you to try this one. What's the noble gas notation for phosphorus? Okay, it's got 15 electrons. Okay, so what you should do is go to the noble gas that appears before phosphorus. That's neon, which has got 10 electrons. So that means we need 5 more, and they fill in 3s2, 3p3. So here are the noble gas configurations for elements 11 through 18. So you can see kind of how that saves having to write all of that out there. Okay, so we've talked about valence electrons before. Those are the electrons that are in the outermost shell. They are the electrons involved in bonding. Only the electrons in the atom's outermost orbitals, which are the orbitals with the highest principal energy level, are going to be involved with bonding, and those will be the valence electrons. So, using phosphorus as an example again, right, here's the electron configuration, or if we want to look at it with neon here, or sorry, as the noble gas notation with neon, the things with the highest principal quantum number, and the highest principal quantum number here is 3, okay? Those 5 electrons that are associated with it there, those are your valence electrons, okay? So this one's going to have 5 valence electrons. All these other ones are in inner shells, so they're not going to be involved with bonding. What about something like arsenic, As? So right here's its electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. Or if we shorten it to the noble gas notation, argon, 4s2, 3d10, 4p3. Well, once again, we're looking for the one with the highest principal quantum number, and here that's 4, okay? These 3d10 are not in the outermost shell, just these 4s and 4p. So arsenic would also have, just like the one before, 5 valence, okay, electrons. And we would skip that 3d because that principal quantum number is not the highest value, okay? We would also say that arsenic is isoelectronic with phosphorus because it looks very similar, right? This one ends with 4s2, 3d10, 4p3. Phosphorus was 3s2, 3p3. And if you get rid of these non-valence electrons, you'll notice how similar these two things look. 4s2, 4p3, 3s2, 3p3. And they're in the same family with 5 valence electrons, right? Family 5a. So you can kind of see how electrons will start stacking on top of, at least their families will have very similar electron configurations stacked on top of each other if you look down at a particular column. Okay, one last thing I would like to point out to you is actually how the families work within the periodic table. You might note here that everything in this first column, okay, ends with, let me grab a different color here, let's end it with blue, ends with S1, and everything in the second column is S2, okay, and then over here, everything in column number 13, or family 5A, ends with P1, and this one is P2, and these are P3 and P4, P5, and with the exception of helium here, everything in this family ends with P6. Helium, of course, is S2. So what you might notice is everything here on these far to left columns end with S orbitals. Everything over here on the far right, with the exception of helium, ends with P orbitals. Well, you might be able to then guess that everything here in the middle columns, these end with D. And everything down here at the bottom, these end with F. Okay, so we might sometimes call this the S block or the D block or the P block or the F block, okay? Those are where those particular electrons end. So you can kind of really see how the periodic table is arranged here once you understand electron configurations and how things fill in.